Welcome students to this next lecture of the Introduction to Algorithms, and today we'll be learning about the growth of the functions. In our last lecture we learnt about space and time complexity of algorithms, and I told you that it is important for us to analyze algorithms so that we can say if algorithm A is better than algorithm B. But the question that should arise in your mind is that if one algorithm is having time complexity of say n and another one is having a time complexity of n square, which one is better and how and why? Okay, so that is what we will try to learn by looking at the growth of the functions. So I will take a small example that if we have two algorithms, one is of time having a time complexity of n and the other one is having n square. Okay, so now the simple question should be which one is better? So you might say that this algorithm is better than the n square because say if we are having n equal to 10, this will take 10 units of time and that will take 100 units of time. But if we see that if n is greater than 2, then this algorithm is good. Okay, means if n is 3, 4, 5, 6, then only this algorithm is good, better than this. If n is greater than 2, I will write here 1 and I will write here 2. If n is greater than 2, 1 is better. If n is less than 2, say n is 1, say then it will be 1 and this will be 1 square, that is 1. At that times they will be of equal time complexities. In another example, you will get a better idea. Say we are having say 104n is one algorithm and the time complexity of other algorithm is n square. So for all n less than 104, as long as n is less than 104, algorithm 2 is better. Means when n will become 104, this will be 104 into 104, that is 104 square, and this will be 104 square. At that time it will be equal. So we cannot simply say an algorithm 1 is better than algorithm 2 just by looking at the leading term. We also need to know about the constants involved with the leading terms. Okay, that's what I want to tell you. But if we are having 2 or 3 algorithms and the leading term is comparable, at that time we can simply see the order of magnitude. We can say that n square is worse than n or n is better than n square. Okay. Now, in previous examples, we saw, say we had, I'll give an example, we had a time complexity n cube plus 2n square plus 3. And I told you that this is order of n cube because we take the higher order term. But what happens is that in certain algorithms, the lower order terms are also significant. Okay, so now we are faced with the challenge of two things. One is identifying the constants associated with the higher order terms, and in some cases even the lower order terms are significant. But that is not practically feasible right here to calculate the constants associated with the higher order terms. What we do is that, as I told you in the previous lecture, that we are having prior analysis. So in prior analysis, we only see the leading term, means the higher order term. And when it will come to the posterior testing, at that time we will calculate or we will see the constants that are associated with these higher order terms. Okay. So I'll give you another example so that you will be able to visualize the need for the comparison of functions or how functions grow. Okay. So for now, we have seen the growth. How? Because if n is greater than 2, means n will be 1, 2, 3, 4, 5. So what's happening? It's growing. N is growing. That's why we call it growth of function. So as n grows, we see 1 is better. And below 2, 1 is not better. Same here, when n is less than 104, means as function is growing and up to 104, your algorithm 2 is better. And once it grows beyond 104, algorithm 1 is better. So we will see another example where you will get an idea that how these functions grow. Means this will give you an idea that how algorithm 1 is better than algorithm 2, or how algorithm can be optimized when you look at its time complexity. Say we are having two algorithms again, 1 and 2. The first algorithm has a running time complexity of n square, and the second one is having n log n. In previous lecture, we saw an example where we saw it had a time complexity of running time complexity of log n. So you have an idea how log n is generated, and n square you know. If you are having two loops, there it will be n square. There are other ways also where we can have n square, but I'm referring to the previous example that we saw. So here what will happen, if we take for n equal to 1024, I'm taking an example where n is 1024. Let me see how these two functions will behave, how these two algorithms will behave. So for 1024, we'll square it and it will be equal to 1048576, and the other one will be 10240. Okay. So I'm just substituting value of n here, I'm squaring it, and here I'm taking n multiplied by log n, okay? And these are the number of the operations that it will take. Now, if we assume that it takes 1 microsecond, if we assume that it takes 1 microsecond for these instructions to execute, the actual time will be 1.05 seconds, and if we multiply here, it will be 0.01 seconds. Okay. So far, we have done nothing. We have simply taken two algorithms. One is having n square time, another is having running time n log n. We are taking an example where n is equal to 1024. So 1024 squared is this much, and n log n means 1024 log 1024, it's 10240. Okay. And then what we are doing, we are assuming that it takes 1 microsecond to execute one instruction, and we are multiplying 1 microsecond with this, we are getting these 1.05 seconds and 0.01 seconds. So now let us see how they will grow. Means we will jump. We will see for n equal to 2048. So what have we done? We have done 2x. We have multiplied it by 2. So we have jumped. So we will see how this will change and how this will change. If it shows any significant difference, we will understand that this function grows in a different way rather than n log n, and we can say which one is better. Okay. So when n equal to 2048, what will happen is that this time will become 4.2 seconds, and that will become 0.02 seconds. So now you can see the difference. This has doubled. Not only doubled, this has gone 4 times. Okay, because this was 1 second, this is 4 seconds. And this has hardly doubled. Okay. So what do you understand by this? What do you get by this? That this one, we know that as n will increase, this will increase and this will also increase. There is no doubt about it. But what happens is that in this case, when n increases, we are having same. It has doubled from here to here, but you can see the drastic change here and a little change over here. So this gives us an idea that different functions, they grow in a different manner. So we need to understand and know how different functions grow so that we will get an idea while writing our algorithms and while analyzing them, that how we should optimize it or when we should optimize them. Okay. So what I will do is that I will write some very popular or standard time complexities of algorithms, and then we will see how they grow. Okay. So I will start with 1, and then we are having log n, and then we are having your under root n, then you are having your n, then you are having your n log n, then we are having your n square, then n cube, okay, then we are having your 2 raised power n, then your 3 raised power n, and finally n raised power n. So these are some standard or popular time complexities, and I have written different functions over here. So you remember this one from the example where we are studying the time, analysis of algorithm, and I showed you we have to calculate the number of times an instruction exists, and it was 1 n and n square. So I told you 1 is the best time complexity because it's constant. So you cannot say this one, you will say if we are having n is 1, at that time it will be equal to this. No, this is something more than that. It means if n is 100, it will still take 1 unit of time. If n is 5000, it will still take 1 unit of time. So this 1 actually means constant amount of time, okay? So then we are having, means whatever your n is, its under root n will be less than your n, and your log n will be less than your under root n, but it will be greater than your constant amount of time. And then when we go towards the right side, if we multiply n and log n, obviously it will be greater than log n, sorry, greater than n, and then n square, then n cube. Up to this point, these are called as polynomial times, okay? So these are polynomial times, and after this, we are having exponential, means 2 raised power n, 3 raised power n raised power n, okay? So now what we will do is that if we want to understand it, just like we saw the example before it, we saw there how n square and n log n were different, you know. N square changed 4 times, while as n log n hardly changed 2 times. So what I will do is that I will draw a small table, and in that table, I will write these values and I will write the values of n, and I will see the behavior of these functions, because that will only give us an idea how they grow. And then I will plot a graph, and on that graph you will get an idea that why we say that log n is better, why do we say that n square is worse, or why do we even say that 2 raised power n or n raised power n for that matter is the worst time complexity, that it's an exponential time complexity and we should avoid it, or we should try to optimize it. So when we talk about optimization, any algorithm that is having this time complexity will be optimized if you turn it into this, or if you write another algorithm that is of this complexity. Anything on the left hand side will be the optimization for that algorithm, okay? So now what I will do is that I will draw a simple table where I will take some values. So what I am going to take is that I am going to take log n, I am going to take n, I am going to take n log n, I am going to take n square, I am going to take n cube, and I am going to take 2 raised power n. So these values, I am going to check what will happen when we have different values of n. So I will begin with 1, then 2, then 4, then 8, then 16, and finally 32. Means when n will be 1, what will be log n, and what will be n log n correspondingly. It is just like the previous example where we saw 1024 and then 2048. Here we are going linearly, so that not rather linearly, it is the multiple of 2, so that we will get an idea how these functions grow. So when n is 1, your log n is 0, your n log n is 0, okay? Your n square, 1 square is 1, n cube is 1, so 2 raised power 1 will be 2, okay? So here you see the difference is not that much significant. Now when n is 2, your log n will be 1, your n log n will be 2, your n square will be 4, your n cube will be 8, and your 2 raised power n will be, that is 2 square will be 4, okay? Still, okay, this you can see here cube has changed drastically, but what about 2 raised power n? That has not changed that much, okay? So now when we will take it as 4, what will happen? Log n will be equal to 2, this will be equal to 8, this will be equal to 16, this will be equal to 64, and this will be equal to 16. So you might be wondering that this is 64 and this is 16, then why have we put 2 raised power n here and we have shown it that it's greater than n cube? It should be less than n cube. But now, as n becomes 8 and 16, things become tricky. So what we are doing, at 8, what will happen? Your log n will be 3, this will be 24, this will be 64, this will be 512, and this will be 256. So still the question remains, this is 256, this is 512. So something seems to be wrong here. But now let's go to 16. So at 16 this will be 4. Okay. So n log n will be 64. This is 256. This is 4096. And this is 65536. Now things have changed. Because whenever we talk about the time complexities, I told you the time complexity is the function depending on the length of the input. Okay? So the length of the input, when we talk about length of the input, we are not talking about n equal to 1, 2, 4. We are actually talking about the higher orders. We are talking about the substantially or sufficiently large n. So we won't be talking about these things. These things, they are almost same. Doesn't matter what time complexity is. We are talking about higher values. And 16 is not that much high, but still you can see here. See the drastic change here. It has jumped from 256 to 65536, and this has not jumped that much. So now things start to get complicated. So for 32, we are having 5, we are having 160, we are having 1024, this is 32768, and look at the last one. It is 42949. 67296. See how much big this number is. I have just doubled n from 16 to 32, and see how these are growing, how this is growing, and look at this one, exponential growth. It has gone out of your hands. Okay? So this gives us an idea about growth of the function, how functions grow. This can be, now you will be thinking that do we need to draw a table and try to understand what happened? No. I will show you a graph while I'll plot these values, log n, n cube, n square, 2 raised power n, and you will get an idea how they grow. So that it will be in your mind while writing algorithm or while comparing algorithm, which one is better. Okay? So what we do is that we plot n with f of n. Means we take different values of n. In the previous example, it was 2, it was then 4, 8, 16, 32. Same way you can take different values of n, and there will be corresponding values from this side. So we will see how they will grow. So the first one is your n. And you know what n does. N is simple. If n is 1, f of n will also be 1. If n is 2, f of n will be 2. So when it's n, it will simply be a straight line. So if you go here, this will be your n. When you are having a time complexity of n, it will be a straight line. After n comes your log n, which we saw is better than n. So what will happen with log n is that it will go something like this. Okay? So your log n is growing something like this. So it will never go, more than n. It will be less than your n. It first grows quickly and then it stabilizes. After log n, we saw n log n. Because we are multiplying n with this log n, so what we will get is that we'll get something that will surpass it, and then it will go like this. So that will be it will actually keep above this n. So if we will draw it more accurately, it should be something like this. It will go like this. Okay, this will be your n log n. So after n log n, we will see n square. Because this is n, it will be squared. It will again be somehow a straight line, but it will be more than this. It will be like this. It will be n square. Okay? And then n cube, again, it will go like this. N cube. So you are seeing how functions are growing. N is growing linearly. Log n a little bit more than stabilizing. N log n still more than stabilizing, and then n square, it's same, n cube is same. But now comes the most critical one, that is your exponential, that is 2 raised power n. You saw what 2 raised power n did. Initially, it tried to act innocent. It didn't show that much of growth. So 2 raised power n, you can say it initially goes small, but then suddenly it jumps. Okay, so this is the sudden jump. See where 2 raised power n is going. It is, you can imagine the slope here. It's almost, perpendicular, and that will give you an idea of the growth of 2 raised power n. Okay, so this is the graph that you will find in almost every standard algorithm textbook, where you can see the different functions and you can see how they grow. We saw the table before this, and now we have seen this graph. So now we will see, towards the end of this lecture, we will see how to compare. How will you know if you are having two time complexities? How do you know which one is better? Okay, what are the ways to compare the time complexities of two algorithms? So one of the easiest way to learn about or to understand how to compare two functions is using logarithms. What we do is that, say for example, we are having f of n, which is equal to n square, and we are having g of n, which is equal to n cube. Okay, so we want to know which one is lesser. Okay, so what we will do, we'll simply apply log. So if we apply log, f of n will become log n raised power 2. This is log a raised power b. This will be 2 log n. Okay, and what will happen to this one, g of n? It will be, if we apply log to g of n as well, it will be log of n cube. Okay, and 3 will come, it will be log of n. So now they are easy to compare. We are having log n, we are having log n. This is 2 times, this is 3 times. Means this is lesser than this. We can say dot f of n is less than g of n. Okay, so this is how we compare two functions. We will see 2-3 examples very quickly how to compare the different functions. So in another example, I am taking f of n equal to, I'll need more space here, so I'll rub it out, is equal to n square log n, and g of n is equal to n log n to the power 10. Okay, you might be thinking the earlier example was easy. What was the need to apply logs? But this example is a little bit tricky. Now you might be scratching your head and thinking, how do I know which one is lesser and which one is greater? So what we do, again, we apply log to both of these functions. Apply log to fn and gn. What will happen is that for f of n, it will be log of n square log n. Okay, so we'll be multiplying it. It will be log of n square. So you know log a into b is log a plus log b. So it will be plus log n. Okay, so this is log a raised power b. This will be 2 times log n plus log n. So now what about g of n? When we'll apply log to it, it will be log of n log n raised power 10. So this is log, this will be log n multiplied by log n raised power 10. So log a into log b is log a plus log b. So it will be log n plus log n raised power 10. Okay. So this log n will remain as it is, plus this 10 will come, because this is log a raised power b, it will come 10 log n. Now log of log n is a very small term. Log n in this equation, log of log n is very small term, but log n is a prominent term. So what we will do, in both of these, we will be comparing the larger term, which is log n. And if you see, here we are having 2 log n, here we are having only 1 log n. So what will be? This one is greater than that one. So your f of n will be greater than your g of n. Fine. So moving on, we'll see another example. Your f of n is 3n raised power under root n, and your g of n is 2 raised power under root n log n. Okay. So now we have to see which one of them is smaller. So what we'll do is that we should apply log, or we can apply log where you think you cannot solve the equation. But if you think that you can solve the equation without applying logs, you can go ahead with it. So I can somehow convert this into this form so that I can compare these two. So there is no need to apply log, you can simply solve it. So if I take this g of n, it is 2 raised power under root n log n. Okay. So you know a, if we are having a log b, it is equal to b log a. Of course, the bases are same, means if you are having here base c, it will be base c here as well. Okay. So we can change this. If it is 2 raised power under root n log n, what we can do is that we can write it as, first we will change this thing, because you know that this is a log b. This is actually equal to log b raised power a. This a can be taken in the power. So it will be 2 log n raised power under root n. Now we are going to exchange these two here. B and a we are going to exchange. So it will be n raised power under root n. Okay. And in the top it will be log 2. So what is log 2? Log 2 to the base 2 is 1. So this is simply n raised power under root n. So now g of n is n raised power under root n, and f of n is 3n raised power under root n. Okay. Okay. So what we can do here, we can say value wise this one is greater than this one. That is true. But asymptotically they are equal, because both are of order n raised power under root n. Then your question should be, in previous examples we had 3 times log n, we had 2 times log n. Why did we say that 3 times log n is more than 2 times log n? Because at that time we had applied log. Okay. Here we have not applied logs. We had simply solved this equation, and by solving this equation we see this is n root n. This is 3n root n. Value wise this one is greater, but asymptotically both are having same, the degree of the higher the higher value or the leading term is same, that is under n root n, n root n. So f of n is equal to g of n asymptotically. Value wise this one is greater. And in previous examples, why we say f of n is greater than g of n or g of n is greater than f of n? Because in those examples we took logs, we didn't solve. If you solve these the time complexities without using logs, at that time if the leading terms have same degree, then they are same. So as in last example, we'll take a very simple example, that is 2 raised power n, and we'll take 2 raised power 2n. Okay. So what we'll do is that we'll apply log. When we apply log, this will become log of 2 raised power n, and it will be n log of 2. Log of 2 to the base 2 is 1, so it will be n. Now on this on this side we are having log of 2 raised power 2n. It will again be equal to 2n log of 2. So log of 2 is 1, this will be equal to 2n. So like I said in previous example, although here both of them, the leading term is having degree 1, that is this is n, that is n, but we have applied logs. Since we have applied logs, we can say that this one is less than this, means f of n is less than g of n, because we have applied logs. Had we not applied logs and we had simply solved this equation, at that time they would have been of equal order, or their time complexities would have been same. So with this we finish the comparison of functions. So in today's lecture what we saw is the growth of function, which is very important. Means that we have learnt the methods to calculate the time and space complexity. We saw frequency count method. But we need to know how we can say that one time complexity is better or worse than the other. For that, we saw these general time complexities. We substituted values. We saw in that table how they grow, and then we saw the graph. In that graph, we saw how these different time complexities grow, and the worst one was the exponential growth. And finally, I showed you that if you are having values which you cannot compare directly, there you have to solve them either using logs, or you can simply solve them so that you can compare them by making them making their leading terms look similar or comparable, and then you can check which one is better or worse. So this concludes our lecture about growth of function. So hope to see you in next lecture. Thank you.